So in the last class, Thevenin theorem was explained to you, and what were the steps involved to solve the numerical problem based on the Thevenin theorem was also explained to you, and also the concept of the fictitious battery while calculating the open circuit voltage or Thevenin voltage was also explained to you based on the polarities of the battery sources. Okay, so the problem which is associated with the Thevenin theorem generally deals with the calculation of load current. Okay, so whenever we talk of the load current or the current calculation in the circuit, we also mean that the its associated properties are also to be taken care of. For example, if we are aware of the current, then the drop associated with the load resistance can also be asked, or the power consumed by the load resistance can also be asked. Okay, so another thing or the demand of the Thevenin theorem is to verify the Thevenin theorem. Okay, so whenever we come across this term, verify the Thevenin theorem, so it is to be dealt with differently. Okay, why? Because as we have studied in the theorem definition, that the current in any passive circuit element in a network is same as would be obtained if RL were supplied with the voltage source VOC, etc., etc. Okay, so it means that the current in the any passive circuit element or the load resistance is same as would be obtained by this method or by any other method. Okay, so whenever we come across the term verify the Thevenin theorem, it means that now our demand is to calculate the load current using Thevenin theorem and also verify the same result using any other method. That any other method can be the nodal voltage theorem or Maxwell's circulating current theorem, KVL, KCL, whatever you feel like. That is up to you. Okay, but since we are in demand of verifying the Thevenin theorem, so the results which are obtained through the Thevenin theorem should match with that of the other theorem. Okay. Okay, let's begin with this solving this circuit which is given. So here two battery sources are given in this DC network and a load resistance in the rightmost section of the circuit is given as 150 ohms. So by and large in the Thevenin theorem, we are required to calculate the Thevenin voltage and Thevenin resistance. So as I have told you, the process to be adopted for calculating the Thevenin resistance is that make short the battery sources. Okay, and suppose this is battery source, it is to be shorted, this is to be shorted, and this load resistance, it should be open. Okay, and the circuit is to be solved by looking into the circuit. This is very important, that wherever the position of the load resistance is, we have to calculate by looking into the circuit. Okay, so when the current is flowing in this direction and we come across this node, so this 6 ohm and 30 ohms will be in parallel, and the parallel combination of these two 6 ohm and 30 ohm will be in series with this 5 ohm. Okay, so same we have used for the calculation, which you can see this 5 ohm is added up in the parallel combination of 6 and 30. Okay, so which we can calculate this Thevenin resistance as 10 ohms. Okay, now you have to calculate the Thevenin voltage. For that we require the current which is flowing in the loop. So again the methodology will remain the same, that open circuit will be across the load resistance. So when this resistance or the load resistance is open, then the current will not flow here. Okay, because open circuit means that infinite resistance. Resistance is infinite, and the property of the current is that it follows the least resistive path. So since there is infinite resistance here, this portion of the circuit is no longer to be considered. So now we are having simple this circuit with only one loop. Okay, so here 30 ohms and 60 ohm resistances are in series, and battery source is 108. So we will be applying the Ohm's law here, and we will get the current 3 amperes which is flowing through this loop in the clockwise fashion. Okay, so after calculating the current, we can calculate the drop across this 6 ohm resistance and this 30 ohm resistance. Since the current flowing is 3, so correspondingly the drops will be 18 volts. 6 3 is 18, and here 30 into 3 90. Okay, okay, is this clear,
Yes,
Purvi?
sir.
Okay, so in the last class I have explained you that these drops can be replaced by the fictitious battery, so that we can get the polarity of the battery and we can use them to calculate the Thevenin voltage or the open circuit voltage if needed. Okay, so since the polarity of this battery source is as shown, so the polarity of these two voltage drops will be opposite to it. Okay, so the 30 ohm resistance can be replaced by a 90 volt, and 6 ohm can be replaced by 18 volts fictitious battery. It is not actually existing, but it is assumed to be existing. Okay, so the polarity of the 30 into 390 volts will be this way. Same will be of 6 into 318. Okay, so this is the case. So now we have to calculate the open circuit voltage, which is the voltage across these two terminals when the load resistance is removed. Okay, so whenever we calculate this, we will be, we can either follow this path or this path. It is immaterial, but we prefer to follow this clockwise path because of the positive terminal of the 110 volts. Okay, so this is also having this polarity, and 90 ohms is also having similar polarity. So this 90 volts and this 110 volts will get added up, and when it goes to this 5 ohm resistance, it was not having any current, so there will be no drop or no battery source or fictitious battery, you can say. So the resultant voltage between the A and B terminals will be 200 volts. Okay, is this clear? So when this voltage is clear to us, then we have to calculate the load resistance and apply the Thevenin theorem, which says that the load current will be equal to the open circuit voltage divided by the load resistance and the Thevenin resistance. Okay, you can say that this Thevenin theorem is now reduced to a simple Ohm's law type of situation, where this is our 200 volts and RT is our 10 ohms, which we have calculated, and load resistance is given as 150. So this 150 and this 10 gets added up, you can say, so it becomes 160. So 200 upon 160. So this is the load resistance, which comes out to be 1.25 amperes. Okay, so is this clear to everyone? Till now we have done the half part of the numerical of calculating the load current using the Thevenin theorem. Now we will calculate the current, same, which is passing through the load resistance, but using any other method. So here we will follow the mesh analysis using KCL and KVL. So this circuit is shown to you. So in this circuit, let us first name the currents I1, I2, etc. as shown. So we will calculate the current flowing in these two mesh. So in the first mesh, let us suppose that the current I1 is flowing. Okay, so when the current I1 is flowing, what happens at C junction? When the current is flowing in a clockwise direction, so this I1 current is flowing, and in the second loop, again the clockwise current is flowing as I2 because of the positive terminal of this battery source. Okay, so when the C node is there, here the KCL will be applied. I2 current is flowing in this fashion. Okay, and I1 current is incoming current and out2 current is the outgoing current. So the current which will be flowing in the vertical branch will be I1 minus I2. Okay. Okay, is this clear? So similar type of problems we have done already. So now by applying the KVL in the first, so if we consider the KVL application in the second loop, we get 5I2 plus 150 I2 minus 30 I1 minus I2 is equal to 110. Okay, we have observed that by following the Thevenin theorem and also using this mesh analysis, we get the similar load current of 1.25 amperes. In the mesh analysis, we were having two equations and two unknowns, I1 and I2. Here I2 is the load current or the current which is flowing through the load. So we have observed that these two currents were identical. So we can say that the Thevenin theorem is verified. Okay. So we will take another numerical here. So a circuit is given to you and the load resistance is R3. What does the question says? The question says the find the current in the R3. So when we are required to find the current in the R3, it means that the R3 is acting as the load resistance. Okay. So first thing first, we will calculate the Thevenin resistance. So to calculate the Thevenin resistance, what we are required to do, so the R1 and R2 which is designated as 2 ohms and 1 ohms will be parallel, because according to the Thevenin theorem, when the load resistance is open circuit, then the Thevenin resistance is to be calculated from the load resistance into the circuit. So the path of the current will be from A to above. Okay, so we will come across this node and here the current division will take place. So we can say that this 2 ohms and 1 ohms resistance are in parallel. Okay, it is similar to the what we have done earlier also, that if there was circuit like this and this is the load resistance, and when this load is open, then we assume that there is a fictitious battery here and which is promoting the current from the load resistance into the circuit. So when it is promoting the load current or the current from the load, it means that the current division takes place here. So we can say that this resistance and this resistance are in parallel. Same concept is applying here. Okay, so we should always focus on concept as well. Okay, okay, now it is clear, Muskan.
Yes, sir.
Ranu, now it is clear.
Yes, sir.
Okay, now we will move further. So the Thevenin resistance is calculated. Now the next step is to calculate the Thevenin voltage. for that we need to calculate the current which is flowing in the circuit. So, and also when the current is to be calculated, the load resistance remains open. Okay, so between the A and B, it will remain open as shown. Okay, so now this is the 6-volt battery, this is the 6-volt battery, and this is the closed path. Okay, and these batteries, the polarities of the batteries are such that they add up or subtract each other. So since the polarities of these batteries are such that they subtract each other, so there will be a zero battery source or zero energy source. So when there is a zero energy source, no current will flow in the network, or we can say that current flowing is 6 minus 6 upon 2 plus 1. Ohm's law is applied, but the current is 0. Okay, so now we have to calculate the open circuit voltage. Okay, so the open circuit voltage is the voltage between the A and B. Okay, the voltage across these two terminals. Now we can take either this circuit or this circuit. In both these circuits, the current flowing is 0. Okay, so the if the current flowing is 0, it means that the voltage across AB will be same as the voltage source which is given. Okay, again in this circuit no current is flowing. So when no current is flowing, it means that the voltage magnitude will be same and the polarities will be such that they cut each other. So it will be a 6-volt open circuit voltage. Okay, so now the things are similar. We have calculated the RT, we have calculated the VT. Now Ohm's law can be applied. This Thevenin theorem circuit is simplified to the this circuit as shown, where we have one voltage source, one load resistance, and one Thevenin resistance. So Ohm's law is applied and the load current is calculated. Okay, is this clear to everyone? Is this clear? Open circuit voltage is the voltage which is across the load resistance. Okay, so we have to calculate the open circuit voltage between A and B. So let us consider this loop. Okay, so in this loop, the current I is already calculated as 0. Okay, so if the current is 0, it means that there is no potential difference. As I have explained yesterday also, if no current is flowing, it means that VA and VB are at same potential or they are equipotential. Okay, same is the case here, that no current is flowing in this loop. So the voltage between the A and B is 6 volts. Okay, and its polarity will be like this, so that it can cut or subtract the polarity of the given 6 volt. Okay, now is it clear?
Yes, sir.
Okay, let's move further. So this is another numerical on same lines. Okay, so here we have to calculate the current through the load resistance 6 ohm using Thevenin theorem. So this load resistance is given as 6 ohms. Okay. So first of all, we have to calculate the Thevenin resistance. Now we are open circuiting the load resistance and short circuiting the voltage source. So current will be flowing here. This node is coming. So 6 ohms and 3 ohms will be in parallel, and its parallel combination will be in the series combination with the this 4 ohm resistance. Okay, so in this way we can calculate the Thevenin resistance. Now we have to calculate the Thevenin voltage. So for that we have to calculate the current which is flowing. So since the A and B terminals are open, so no current will flow in the 4 ohm. Now we have to focus on the first loop. So in the first loop, the resistances 6 ohm and 3 ohm are in series, and the battery source 15 volts and 6 volts are such, their polarities are such that they cancel each other. Okay, subtract each other or decrease the magnitude. So the effective voltage in this loop is 15 minus 6, and Ohm's law is applied. So 9 upon 9 is 1 ampere. So we have the current which is flowing through this 3 ohm and 6 ohm, and it is 1 volt, 1 ampere. Okay, so now we have to calculate the voltage, open circuit voltage or the Thevenin voltage between the A and B terminals. Okay, so what we have to do, this voltage across this will be same as the voltage across this because of the parallel nature of the circuit. So 15 volts is given, and these drops across the 6 ohm and 3 ohm can be replaced as the fictitious battery, and the polarity of the this 6 ohm is immaterial to us because we are concerned only with the parallel combination, because the voltage across this parallel combination will be same as across the AB. Okay, so the the polarity of the fictitious polarity of the battery, yeah, polarity of the fictitious battery will be okay. Okay, is this clear to you? So this 3 into 1, which is 3 volts, and this 15 minus 3, so it will be effective voltage will be 12 volts. Okay, so 12 volts is here, so which means that open circuit voltage is also 12 volts. And now we can apply the Ohm's law, which is the open circuit voltage 12 volts, load resistance 6 ohms, Thevenin resistance 6 ohms. So 6 plus 6 becomes 12, and numerator is also 12. So the load current is 1 ampere. Is this clear to everyone?